and welcome to week 3 of an introduction to paleontology with the Safe Cultural Heritage Group. As always, I'm Jenny, your mentor, and this week we will be studying the Devonian fish and the water to land transition. You will be learning about what they were, key dates, palaeogeography and palaeoclimate, key fauna, key localities, as well as the fin to limb transition, key organisms and the evidence for them. Our story in the Devonian, which is 419.2 to 358.9 million years ago. The Devonian was also known as the Age of Fishes as well as the Age of Sharks, and this is just due to the huge amount of fish that started to diversify in the Devonian. During the Devonian as well, it was the first radiation of life on dry land, which included free-sporing vascular plants, arthropods and tetrapods. Palaeogeography and palaeoclimate like in the Devonian. So the palaeogeography was dominated by the supercontinent Gondwana in the south and Siberia and Euramerica to the north. The sea levels were extremely high worldwide, with the Panthalassa ocean covering the planet. It was relatively warm and it was thought to have lacked glaciers at the poles. The sea surface temperature was an average value of 30 degrees centigrade in the early Devonian. As well as this, CO2 levels dropped due to the forests forming. And by forests, we don't mean like the plants that we see today. Fish up into two different groups. We've got the Agnathans, which means the jawless fish, which include the extinct Heterostraci, as well as the group of family that includes lampreys and hagfish. We've also got the Gnathostomes, which means jawed fish, and these include the Osteichthyes, which are the bony fish, which we are all descended from, Chondrichthyes, which are sharks, rays and chimeras, the extinct Acanthostega, as well as the extinct Placodermi. We will be going through all of these in this lecture. And with the Agnathans. So Agnathans means jawless fish, and it's the Greek for without jaws. It consists of both present and extinct species, with present being the Cyclostomes and the extinct including conodonts and ostracoderms. Its peak diversity was during the Cambrian to the Devonian, and the oldest fossil Agnathans appeared in the Cambrian. Cyclostomes, which are lampreys and hagfish, are sister to all known jawed vertebrates known as the Gnathostomes. And often hear the term ostracoderm, and what ostracoderms are, it's an artificial designation of distinct superclasses of jawless fishes. And ostracoderms it is kind of a paraphyletic taxon, which is kind of, so it means old armoured jawless fish from the Paleozoic. The first order that we'll be looking at are the lampreys and the hagfish. So lampreys, the earliest fossils were around 360 million years ago, whereas for hagfishes, the earliest fossils were around 300 million years ago. We know that there was roughly a divergent time of the lampreys and hagfishes at 470 to 390 million years ago. And they are the only extant species of Agnathans. So these two families are known as the Cyclostomes due to their round mouths as seen in that picture. They are characterised by an absence of paired fins as well as the presence of a notochord both in larvae and adults. Extant hagfish are morphologically similar to the hagfish from 300 million years ago. So they haven't really changed much within those 300 million years. And then lampreys are more closely related to gnathostomes than they are to hagfish. The second family we'll be looking at are the Heterostraci. These are kind of armoured fish. They have head shields and have generally around 2 plates on its dorsal side and one on the ventral side. So one here and one here. Well, one here and here. They also didn't have fins besides the caudal fin, which is their tail. There's over 300 species of Heterostraci, and the first identifiable Heterostracans were in the early Silurian. They also became extinct by the start of the late Devonian in the late Devonian mass extinction. They varied greatly in body morphology, and their scales that have been found have 3 layers composed of dentine and aspidine. Dentine is what we have in our teeth. There are 4 groups of Heterostraci. Aspids were jawless fish and were restricted to the Silurian. However, there are some doubtful species that occur in the late Devonian. Roughly, there are only 20 species, ranging from both the Silurian and Devonian. They lack extensive bony plates, so instead they had small, weakly mineralised scales with a row of scutes running down the dorsal side, which we can see in that image on the slide. And their remains have been mostly found in marine sediments, kind of suggesting that they're a marine-only fish. Move to the Thelodonti, and what they are we kind of know from primarily isolated scales in the Ordovician, as well as abundant scales and sometimes whole specimens in the Upper Silurian and Lower Devonian. They lived in both freshwater and marine environments, and the way we can distinguish them from the other jawless fish is because they're covered in distinctive small spiny scales, and these scales are a lozenge shape and they are concave, and they think that these scales might have evolved independently throughout all different species. Pteraspidomorphs are known for their massive dermal head armour, as well as having large ventral and dorsal plates. They range from the early Ordovician to the late Devonian, and their head comprises 40 to 50% of its overall body length. Most pteraspidomorphs lived in marine settings, but they would have lived very near to the shore, including lagoons and deltas. The pteraspidomorphs don't have any paired fins, and they had very flat bodies, which suggests that they are, or they were, most likely to be bottom dwellers. The final family of Agnathans we'll be looking at are the Osteostraci. There are over 200 species of Osteostraci, and they're first seen in the fossil record in the Ordovician, but they radiated greatly in the Silurian and early Devonian. They had an average size range of around 20 to 40 centimetres. The reason why Osteostraci are so important is because they are the first vertebrates to have paired fins, and it's thought that they are probably the most advanced of all Agnathans. They have heavily armoured head regions with a single plate, and on the head have very closely set eyes. They are also considered to be the sister taxon of all jawed vertebrates. The first fossil jawless fish, whose internal anatomy were described in details, were Osteostraci, which I just think is a really exciting fact, really. Now move on to the Gnathostomes. So Gnathostomes are jawed fish, and the gnathostome in Greek means jaw, mouth. They first evolved during the Middle Ordovician, and there's roughly 60,000 species, which account for 99% of all living vertebrates. And they're traditionally broken into 3 different groupings: the Chondrichthyes, the Placodermi, and the Teleostomi. Look at this really useful phylogenetic tree. We can see that the Gnathostomes are really important as they break up into loads of different things, including the sharks and rays, the ray fin fish, the lobed fin fish, and which then led on to our own evolution. Start with the placoderms. And the most famous example of a placoderm is Dunkleosteus, which is this big boy over here. And what these are, they are the first vertebrates to have paired pelvic fins. Their fossils are primarily the armoured plates that are found, and these are roughly the head and shoulder regions, and these were covered by articulated armour plates. And this means that because they're articulated, it means that these plates could move with the body. The first identifiable placoderms appear in the fossil record during the early Silurian. However, during the Devonian, the placoderms inhabited both freshwater and saltwater. Unfortunately, most placoderms went extinct during the late Devonian mass extinction. Looking at the Chondrichthyes, and these are sharks and their kin. And what Chondrichthyes are, they are the cartilaginous fish. There are two subclasses, the Elasmobranchi, which are sharks, skates, rays and sawfish, and the holocephali, which include chimeras. The first definite remains containing cartilage date from the early Devonian. And for Chondrichthyes, the major lineages arose in the Devonian and radiated throughout the Carboniferous. There's a great fact that we talk about in paleontology where sharks are older than trees, and they've survived every mass extinction that has ever happened. And I just think sharks are really cool. Looking at the Osteichthyes, these include both the Actinopterygii and the Sarcopterygii, which are the ray-finned fish and the lobe-finned fish. With the Actinopterygii, so these are the ray-finned fish, and Actinopterygii is Greek, actino is having rays, and pterygia is wings. And we have, they are the extant ray-finned fishes. We have around 27,580 species, and there were only 15 genera during the Devonian. And Actinopterygii are kind of like the fish that you would picture when you picture a fish. So, for example, pufferfish, piranhas, lionfish, salmon, trout, tuna, any of that are Actinopterygii. The first examples were from the early Devonian, and these were represented by just scales. And then we find that there was a diversity of Actinopterygii during the late Devonian and the Carboniferous. The earliest known fossil Actinopterygian is the Androlepis hedii, which was dated from the late Silurian. We'll move on to the Sarcopterygii, and these are the lobed-finned fish. Sarcopterygii in Greek, sarco equals flesh, and pterygia are wings. And they have fleshy pectoral and pelvic fins that articulate with the shoulder and the hip girdles with just a single bone. So, for example, in tetrapods, which include us, the shoulder connects to the humerus and the pelvis attaches to the femur. There are extant species of Sarcopterygii, which include the Actinista, which are coelacanths, the Dipnoi, which are lungfish, Tetrapodomorpha, which are a clade of vertebrates which consist of tetrapods, and the Sarcopterygian relatives, which are more closely related to us than they are to the fish. So, what was the water-to-land transition? It's the transition of vertebrate organisms in the late Devonian epoch. So this transition had already occurred in the plant and invertebrates, which allowed for the establishment of suitable habitats. The fossil record of this transition in tetrapods is extremely poor, and so this posed numerous questions to paleontologists, and the water-to-land transition itself posed numerous physiological challenges in early tetrapods. Before, the key dates for this were primarily in the late Devonian, which was 382.7 to 358.9 million years ago. The tetrapod evolution occurred during the Famennian stage in the Devonian, and the first tetrapods appeared in the late Devonian around 367.5 million years ago. And there was a big mass extinction at the end of the late Devonian, which led to 2 substantial extinctions of marine animals. Originally, the transition between lobed-finned fish and tetrapods were unclear, and this is because the fossils of the earliest land tetrapods that had fully functioning 4 limbs for life on Earth was around 363 million years ago, and the fossils of lobed-finned fish occurred at 390 to 380 million years ago. So we had a gap of roughly 20 million years where we weren't sure what happened evolutionary-wise between the lobed-finned fish to become early tetrapods. With Eusthenopteron, which was a late Devonian lobed-finned fish. It was 1.8 metres long, and it had similar features to the earliest tetrapods, in terms of its fin configuration, which included the humerus, the radius and ulna, and digits. Roughly 2,000 Eusthenopteron specimens have been collected from Miguasha, with a hamlet on the east coast of Quebec in Canada. With Eusthenopteron was strictly aquatic. We're going to look at Panderichthys now, which is thought to belong to a sister group of the earliest tetrapods. It was a late Devonian organism, and it was roughly 90 to 130 centimetres long. And Panderichthys is interesting because it shows a range of transitional features between lobed-finned fishes, for example Eusthenopteron, and the earliest tetrapods. And it's interesting because we found fossilised trackways in 2010 of Panderichthys, and we believe that it isn't a direct ancestor of tetrapods, but it shows traits that evolved during the fish-tetrapod evolution. On to Acanthostega, and this was another lobed-finned fish from the late Devonian, roughly 365 million years ago, and it was roughly 1.8 metres long. It had very similar features to the earliest tetrapods, but it did have a broader, shortened skull than Eusthenopteron. And Acanthostega is interesting because it had 8 digits instead of 5. So we kind of think that there's a magic ratio for digits, which is 1 bone, 2 bones, lots of bones, and then 5 digits. However, Acanthostega had 1 bone, 2 bones, lots of digits, and then lots of bones, and then 8 digits, which were linked by webbing. And it also lacked wrists, so we sort of think that it was primarily aquatic. We'll move on to Ichthyostega, which is one of the first tetrapods that was found in the fossil record. It dates to the late Devonian, roughly 363 million years ago, and it was 1.5 metres long. Ichthyostega could have moved on land, and it would have kind of moved like a mud skipper would if you've ever seen videos of them. And we think that its hind legs could not support the body. It's also quite interesting because its lungs were surrounded by large overlapping ribs. Ichthyostega followed this bone structure in its hands of 1 bone, 2 bones, many bones, but then it had 7 digits, which is quite interesting. The problem is we're still missing that transitional fossil between the lobed-finned fishes, for example Eusthenopteron, and Ichthyostega, which were the first land tetrapods. Changed in 2006 when this guy here, Neil Shubin, found probably the best transitional fossil that could ever be found. He went into Ellesmere Island in Greenland and Canada, and he found Tiktaalik. This is Tiktaalik. It was considered the missing link between fish and tetrapod, hence why it's sometimes called a fishapod. It shows both fish and tetrapod characteristics, and it was found in late Devonian rocks of roughly 375 million years ago, which is roughly slap bang in the middle of that gap that between lobed-finned fish and tetrapods, tetrapods on land, and it was roughly 1 metre long. Multiple specimens have since been found since that great fossil was found, and we think that Tiktaalik was able to come onto land. And the great thing about Tiktaalik is that it follows Owen's structure of one bone, two bones, many bones, and then digits. Look at this 3D scan of the skull. It's just so cool. Like, we got full, the fossil that was found was just the full skull. We've got teeth, and now because we've got multiple specimens, we were able to build up a body plan. Slide. Tiktaalik was the intermediate between fish and a primitive land-living animal. It showed both characteristics of both fish and tetrapods, making it a really important find. We just have a very rough phylogenetic tree containing Eusthenopteron, Panderichthys, Tiktaalik, Acanthostega and Ichthyostega. Unfortunately, some problems with life on land, and these include reproduction, respiration, feeding, airborne versus waterborne sound reception, locomotion, as well as supporting its body mass on a less dense medium than water. The further reading, I will link these in the comment underneath this. I cannot recommend enough Neil Shubin's 2008 book, You're in a Fish. Alongside this, I often really listen to Paleocast podcasts where they've done episodes on Tiktaalik with Neil Shubin, as well as the fin to limb transition. You can also stream Neil Shubin's You're in a Fish documentary, where he kind of goes step by step through the book. And there's also other books that have been written on the fin to limb transition. Next week, we'll be looking at the rise and fall of dinosaurs. So we'll be looking what dinosaurs were, the key dates, Palaeogeography and Palaeoclimate of the Mesozoic, key fauna, cultural depictions of dinosaurs, and the theropod to bird evolution, as well as the end Cretaceous mass extinction. So thanks for watching. You can find Safe Cultural Heritage Group at all of these links, and you can also find me on these. I look forward to seeing you all next week.